Welcome back. In this video, we're going to take the ideas about what a group is that we talked about last time, and we're just going to run through a number of different examples just to place it in a bit of context that might be a bit more familiar. Some of the examples we'll check the axioms quite carefully for, and some of them we'll just sort of discuss in passing because they can be quite straightforward. So we'll dive in and we'll look at a few different ones, and hopefully by the end of this video, you'll have a slightly clearer picture of some standard groups that we'll work with quite a bit. Okay, so we'll start with the one that we used for our big example in our previous video, or one before that, and this is the dihedral group of order 2n. So dihedral groups, they are just the groups of symmetries of regular polygons in the plane. So we did D4 last time, which was the group of symmetries of the square. So remember, a symmetry is just where you pick up the object, transform it somehow, like flip it over or rotate it, put it back down in the same spot, and that particular transformation is one of the members of the group. So for our square, we had R0, R90, R180, R270. Hey, there were 4 rotations, and then there were also 4 reflections. And we just gave them names H, V, D, and D prime, but I'll just write them down as 4 reflections here. Okay, so the group, the dihedral group itself, is the group, the set of these 8 transformations of the square, and the group product, or the group operation, is the composition of these transformations. Now these groups work for any regular polygon, so we could do it for a triangle. That would give us D3. We'd have 3 rotations, that'd be R0, R120, and R240. And again, 3 reflections, this time they'd be along these symmetry lines here. If I draw my picture better, it would help, but you can see there'd be three reflections. Okay, and likewise, you can construct any of these dihedral groups for any regular polygon. Okay, so we get a D5, D10, whatever. The thing just sort of generalizes. So in all these cases, the group members are the transformations or the symmetries of the object, and the group operation is the product. Okay, the identity is always R0. It's always R0. Inverses, well, for the rotation, you can tell which one it is. It's the rotation in the opposite direction. So, for example, in our dihedral group of order 8, i.e. D4, the inverse of R90 is R270, which could also be written as R-90 if you liked. So that's the inverse for rotations, and for reflections, the inverse is just itself. And reflections are their own inverse. Okay, now we didn't check associativity last time, but associativity just comes because we're dealing with function composition, and function composition is always associative. Okay, so these transformations are actually functions, and whenever we're composing functions, that's automatically associative. Okay, so that's all we really want to say about the dihedral groups now. We looked at it in a bit more depth last time, so yeah, we'll just move on. The next set of numbers that I want to look at is the complex numbers. Now there are several groups that we can build out of complex numbers. We'll start with the simplest one, and that is just the set of complex numbers under addition. Okay, so if we've got complex numbers a plus bi and c plus di, we can check the closure of this, i.e. the addition is a binary operation, by just adding the normal way. And you can see we get another complex number back out. And so our operation is closed, and so it's a binary operation on the complex numbers. Okay, so the identity is 0, because if I add 0 to any complex number, I get it back. What about inverse? Well, the inverse is a plus bi inverse. Now, inverse is a bit of a bad term here because, bad notation to use as inverse when we're using addition. So what we'd normally use is additive notation, and so we'd use the negative sign, which is very, very suggestive of what the inverse actually is, which is negative a minus bi. Because if I add that to a plus bi, I'll just get my identity 0 back. And again, associativity comes for free because we already know that addition is associative, and we just have regular addition of the real and complex parts of our numbers. Okay, what about if we took the complex numbers under multiplication? Is that a group? So same set, now we're using complex multiplication as a group operation instead of complex addition. Well, if I think about that for a second, it's not going to quite work. Closure is definitely going to work. Check. We know that we can take two complex numbers and multiply them together. And what will we get? Well, we get AC minus BD for our real part, and then we'll get AD plus BC for our imaginary part. So it's definitely closed. Again, identity. This time we're looking for something that leaves an element unchecked, unchanged when we multiply by it. So this time our identity is 1. If I take A plus BI times 1, I just get A plus BI. So our identity is 1. Give that a tick as well. Okay, inverses. Well, that means we have to divide by a complex number. So what is the inverse? So we have A plus BI divided by C plus DI equals 1. Sorry, times. What am I doing? Ignore that last little moment. We're looking for a complex number C plus DI such that when we multiply them together, we get 1. All right, well, you might remember something about complex conjugates being useful here. So you can check that C plus DI is simply the complex conjugate of what we had before. Now if I multiply that by A plus BI, I'll get A squared plus B squared. So that's not quite what I want. I want 1, so I'm going to have to divide by that factor of A squared plus B squared. So that is the inverse of A minus BI. However, this causes a slight problem because we have the number 0 in our set of complex numbers, and 0 does not have an inverse. And one of the fundamental rules of groups is that every element must have an inverse. So we actually have to exclude 0. So what we talk about instead of C, we talk about C star, and that is 0 excluded. Okay, now once we've taken an element out of a set, we have to just be a little bit careful that we haven't accidentally broken closure, because if it were possible to multiply two non-zero complex numbers to get 0, that would be a problem because 0 is no longer in our set. However, hopefully you can convince yourself that the only way to get 0 is to multiply by 0, and so taking it out is not going to upset the closure of our set. Okay, now we can also take groups within groups here. So you could check, for example, that this set here is also a group, just the set 1, negative 1, I, negative I, under multiplication. Alright, so this is a group that is contained within the group of positive or non-zero complex numbers under multiplication. You can check closure. Multiplying any pair of those together gets you another one of them, and likewise you can find inverses quite easily, ones that where the identity is going to be 1 as it was before. Okay, so we'll talk about subgroups a bit later on, because studying how groups fit together, how one group fits inside another can be quite an interesting thing to know about. But in the interest of time, we're just going to move on for now and plow ahead. Our next example, now we're going to look at rational numbers, largely just to introduce the symbol Q to you. So Q means rational numbers, and rational numbers are just numbers that can be represented as a fraction of integers. Okay, and if we're talking about the positive rationals, like we are here, then we can, without loss of generality, assume that A is greater than 0 and B is greater than 0. Okay, they could both be negative, but we don't lose anything to assume they're both positive. Okay, so closure. If I were to take two such rational numbers and multiply them together, I would get AC over BD, which is greater than 0, and hence AC over BD is a member of the positive rationals. Okay, so multiplication is a binary operation on the positive rationals because there's no way we can multiply two positive rationals together and get something that is not positive and not rational. Okay, the identity, that's just going to be 1. Again, we're multiplying, so 1 is usually the identity when we're multiplying with numbers. And 1 is a rational number, and it's positive, so that's all good. What about inverses? Well, compared with our complex number example, this one's quite straightforward. The inverse of A over B is equal to B over A. This is just the reciprocal. And that is also greater than 0. We can't take a reciprocal of a positive number and get -1. So that means that's also an element of Q plus. And so associativity comes for free because multiplication we already know is associative. So the positive rationals form a group under multiplication. Okay, and for our next trick, we're going to look at the integers under addition. We've already done that one, but now we're going to use addition modulo n. Okay, so that means that we take our integers, so let's just say we look at addition, e.g. z4. Okay, so it's the set of all integers mod n, and we represent it by just the set 0, 1, 2, or 3. When you're working with arithmetic modulo n, you basically take your regular integer and you add or subtract multiples of n until you get yourself into this range. And that gets you the member of the set. Okay, so we're adding, and these are our elements, and the rule is we need to find an identity. We need to check it's closed. So why don't we just draw a Cayley table for our integers. So remember, the Cayley table is just like the group operation table where we look at what the combination of each thing is. So 0 plus 0 mod 4 is going to be 0. 0 plus 1 is 1. 0 plus 2 is 2. 0 plus 3 is 3. Likewise down this column, the zeros are easy. Now, none of these we had to modify because they all fit nicely between our 0 to 3 range automatically. Now we add 1. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. And then I subtract 4 off to get us back into this range from 0 to 3. And so that's 0. This is modular arithmetic, or clock arithmetic if you like. 2 plus 1 is 3. 2 plus 2 is 4, which is 0. 2 plus 3 is 5, which is 1. 3 plus 1 is 0, or 4, which is 0. 3 plus 2 is 5, which is 1. 3 plus 3 is 6, which is 2. Okay, so let's think about what the identity is. Well, when we're adding numbers, the identity is 0. Okay, if I add 0 to any number, I get the same number back. Therefore, 0 is my identity. Okay, inverses. The inverse of A is equal to, well, let's see, what is the inverse of 1? Well, if I just go to my Cayley table, I go to my 1 row and I find the 0 and the corresponding number is 3. And so I have 1 plus 3 equals 4, which is 0. So essentially I got it by starting at 4 and taking away my number. So here for Z4, my inverses is going to be 4 minus A. Does that work for everything? Well, the inverse of 2 would have to be 2 by this rule, and indeed it is. It's its own inverse. The inverse of 3 would have to be 1. That works, and the inverse of 0 is 4 minus 0, which is 0, once we correct it. And again, associativity comes with addition. Now, one of the things you're going to have to do reasonably frequently in this course is to just do modular arithmetic quite often. So in your first assignment, we will be looking at some of the rules regarding modular arithmetic, whether you can multiply or divide, how multiplication works, because generally speaking, you can work with the regular integers, but you can always shift yourself back into the range, for example, 0 to 3 for Z4, at any point during a calculation when it's convenient. And that can save calculations getting quite tedious and large, because you can keep bringing it back into this range. But we'll explore how that works in an assignment. For now, we're just going to keep on chugging ahead. Okay, does the same thing work for multiplication mod n? If I want to look at the set of integers under multiplication, can I just do the same thing I did with addition, and will it just work? Well, let's just maybe slow down a little on this one and be a little more careful about it. So first off, let's just start with the easy things. So I'm going to look at the same set of numbers, so e.g. 0, 1, 2, up to n minus 1. Closure. Well, if I multiply any two numbers together and then translate them back into this range, you can see that the set is closed under multiplication. So, tick. Closure of that set is closed under multiplication mod n, and so we have our closure straight away, which is a good thing. The identity. Well, again, we're multiplying. 1 is usually the identity. 1 is included in our set, and so yes, we can verify that we have the identity, and that's all good too. Associativity also comes for free because multiplication is associative. So I'll give that one a tick straight away. And now we'll get to the slightly curly question, that of inverses. Okay, so if I take a number a in my set, a be a member of 0 up to n minus 1, I want to find the inverse of it. And what does that mean? That means, and I'll call it a times b has to be equal to 1 mod n. Okay, remember the mod n thing just means it's actually equal to 1 plus or minus some multiple of n. So I could say, or equivalently, AB plus some number of n's is equal to 1 for some k. Okay, so now's where we need to just remember what we know about statements like this one here. This is one that we need to know on sight because that gives us some really useful information about the relationship between our numbers. This here says that anything in the left term and any term in the right term are going to be relatively prime to each other. Okay, because when we take, let's just make a little working space up here. If I take integers a and b, and I take a linear combination of these by multiplying by some other integers s and t, so I can do this for a variety of different ways, but the smallest number that I can produce on the right, that is the greatest common divisor of those two numbers. Okay, so smallest number, in fact let's just call it k up here, the smallest possible k is the GCD of a and b. Okay, and because we've got 1 here, that means the greatest common divisor of a and b is 1, which means they have no common divisors other than 1, and so they are relatively prime. So we can, if we look at this formula over here, we can choose any of the integers in the expressions to take the role of a and b that we like. So this in particular means both a and b are relatively prime to n. Okay, so I'm using n for b, this formula b, I'm using n, and on the other side I'm using a or b, it doesn't matter which one. Okay, so this means that I cannot actually have this whole set here because those numbers are not all relatively prime to n. I'm only allowed to have numbers that are relatively prime to n, otherwise I will not have an inverse. Okay, so this means set is actually and we denote it by capital U of n, is the set of all a such that GCD of a and n is equal to 1. Right, so if I were to look at, for example, e.g. U of 12 is going to be the numbers 1 is relatively prime to 12. 2 is not, because 12 and 2 share a common factor of 2. Likewise, 3 is not, because 12 and 3 share a common factor of 3. And 4, likewise. The first one is 5, or the next one on the list is 5, because 5 and 12 have no common factors. 6 and 12 do, they have a common factor of 6. 7 and 12 do not. 8 and 12 have a common factor of 4. 9 and 12 have a common factor of 3. 10 and 12 have a common factor of 2. 11 and 12 have no common factors, and that's the end of my list. Okay, so our set of integers under multiplication that we could possibly have is just this shorter list here, which is the numbers relatively prime to 12 or to n. Okay, but once again, we have done this thing where we have taken some numbers out of our set, and now the problem is it may not be closed anymore. So this tick on our closure has now become a question mark, because what if I multiply two numbers relatively prime together, or to 12 together, do I actually get one back that is also relatively prime to 12 or not? We actually need to check this now. So now we need to recheck closure. Since we've removed terms. Okay, so if a and b are in U of n, is a b in U of n? Okay, so for a, b in U of n, we require that the product is also in U of n, i.e. that the greatest common divisor of a, b, and n is equal to 1. Okay, well, how we check this? Well, the most sort of sensible way of doing it is just to think about the prime factors of a divisor that there might be. So we're going to say, all right, let's assume that there is some common divisor of a, b, and n, and that it's not necessarily equal to 1. So let C be a common divisor of a, b, and n. And let P be a prime factor of C. Okay, so remember, C is a common divisor. It's going to be an integer. Every integer can be broken down into its prime factors. So essentially we're saying, let's just pretend C is prime and see what happens. So we're letting P be one of the prime factors of C. Then P divides N and A or B. Okay, it has to. If C divides AB and it divides N, then its prime factors have to appear in N and have to appear in one of A or B. But we know that N and A have no common factors other than 1, likewise N and B. So actually that means that P is equal to 1 and AB is therefore, if P is equal to 1, it means the only prime factors that C can have are just 1. Therefore C must be 1 also. Let's just write that before we jump to our final conclusion. And thus C equals 1, and therefore the GCD of AB and N equals 1. And finally, that means that AB is a member of U of N. Okay, so that's good. So we've discovered that this set of numbers that is relatively prime to N is closed under the group operation. So, and we know that it's got an inverse, we figured that out. We know that the set is associative, we know the identity is 1, that's always still included. So we do have a genuine group here. Okay, and this is one that we'll use quite often because it's quite an interesting one with some interesting structures involved with it. Cool. Okay, and we're running short on time. But the last one that I want to talk about are some examples of some groups of matrices, because groups don't apply just to numbers, they apply to all sorts of mathematical objects. So if we have a matrix, let's just look at e.g. 2 by 2 invertible real matrices. Okay, and we'll give this a name that you probably won't have seen before. We say that is called the general linear group of 2 for the size, and then R for the types of numbers that are inside it. Okay, this is the field over which it acts. Now, you haven't learned about fields yet, but that's something you'll learn about but later on in the course. So 2 by 2 invertible real matrices. If I have A and B from this set, then I have that because they're invertible, det A is not equal to 0 and det B is not equal to 0. Okay, now I want to test closure. So here's an example of a closure test where we actually have to check that some property holds. Okay, so the set of 2 by 2 real matrices is a bigger set than the set of 2 by 2 invertible ones. So we need to check that the 2 by 2 matrix I get when I multiply A and B together is going to be invertible also. So to do that, the determinant of A times B is equal to det A times det B, which is not equal to 0 by virtue of the fact that det A and det B are both not equal to 0. So AB is also an element of the general linear group. Okay, inverses, well, we've said they're invertible, so inverses clearly work. In fact, we have a formula for that. The inverse of a matrix is 1 over its determinant, AD minus BC, and then we just going to switch over the diagonal entries and make the off diagonals entry, negative, sorry. Okay, and associativity can be checked yourself. Check. Okay, so I'll leave that one as an exercise, but matrix multiplication is associative, and you can test it on in this small case if you like. But it's a bit tedious, involving lots of messy calculations. Okay, so we've got inverses. Check. Identity is just going to be exactly the same identity that you've met before with matrices, 1, 0, 0, 1. And that all works. Okay, so we can't multiply two invertible matrices together and get a non-invertible one, and so we have that matrix multiplication is a binary operation on this set. Okay, other things to note, AB does not equal B A in general. So this is not abelian. Okay, for some examples it does, but generally speaking it doesn't, and so we don't have an abelian group here. Alright, that's one of them. Let's just mention one other while we're still here. The special linear group, 2 by 2 matrices with real entries. That is the set of all matrices A. We'll put them in the general group to start with, such that the determinant is equal to 1. Okay, this one is called the special linear group. And it's special because the determinant of these matrices is equal to 1. So you might call this the volume preserving group or something like that if you like, but it's usually known as the special linear group. Okay, and I'll leave you guys to check some of these properties as an exercise, but you can, if you think about it, if we take two matrices with determinant 1 and multiply them together, then by this determinant formula here, the determinant of the product will also be equal to 1. And similarly, remember that the determinant of the inverse of a matrix is just equal to 1 over the determinant of the matrix itself. And so the inverse of a matrix from the special linear group will also have determinant 1, because that will just be equal to 1 over 1. So it's not too hard to verify that one works, and so special linear group also forms a group under matrix multiplication, which fits inside the general linear group, just much like our 1 and I type example fit inside the complex numbers earlier on. Okay, you can also take matrices over fields other than real numbers. You can put complex numbers in them. You can put integers in them, modulo certain amounts, and I'll let you guys have a look at the study guide in the textbook for how that works. But there are lots of different choices you can make for what types of numbers actually go inside your matrices. Okay, so I think that's enough for one video. It's got quite long. So yeah, we'll leave it there. And next time we'll start picking up some of the properties that all groups have in common. Okay, so we're going to start looking at some theory that applies to every single group, like the one we did at the start with the unique identity. And we're going to see how far we can go just at proving things about groups in general.